Hello everyone. I guess we're about to start. Okay, that's exact time. So I hope you're not getting tired at the end of the conference. My name is Vitaly, and today I'm going to talk about lazy QObject tree traversal. So first of all, a few words about me. I've been doing software for quite a while, and now I'm working as a software engineer here at Cisco Norway. Before that, I was developing Qt, both UI and core network parts. Then working on geospatial software for mass modeling, VFX software, which means visual effects for post-production. And I also hold PhD in geoinformatics from Moscow State Mining University. Yeah, that's it about me. So, and what's the plan for today? First of all, I'm going to share a bit about Qt framework / library and which part QObject takes in this framework. After that, I'm going to show how traversal is implemented in the framework. Then give brief introduction to coroutines and ranges, and then implement or show how to implement lazy tree traversal with using those modern approaches. And at the end, I'm going to share some benchmarks I performed. So regarding Qt, what's Qt? Qt is a framework, and toolkit and a library depend on which level you think about inversion of control. Toolkit because it's not only providing modules, but there's also a collection of tools like linguist and meta object compiler, UI generators, and so on. Qt is open source. All components are open source, but there are some products developed by Qt company like Qt for MCU, for example. They are commercial. So it's cross-platform. At least might be used for 3 major platforms and some minor. There are a few commercial and that's one commercial and few free licenses. So it's like LGPL v3 and GPL and also pure commercial. And Qt is mainly used for UI development, but as I mentioned before, there are a lot of different modules, like for example, STA-like library or libraries for network programming, working with file system, and many other components. So QObject for now. QObject is kind of fundamental component of the Qt, as Qt documentation mentions. So it's kind of heart of Qt object model. A lot of mechanism in Qt relies on this object, this class. It's a garbage collection, so I will show before what it means, but basically all children of current QObject will be automatically removed when a root object is disposed. It also used in Qt meta object system. As we know, there is no proper reflection and meta system in C++ itself so far. There are a few libraries implement reflection of some sort, but well, it's not what we can get on the language level, and Qt one of them. So it also used in the properties mechanism, like regular properties in other languages, so for example C#, and also used in slot signals mechanism. So slot signals, it's kind of observer or subscriber mechanism. Objects might emit signals, and then you can subscribe something or attach something to this event and react somehow. So now QObject trees, what are they used for? As I mentioned before, for garbage collection, of course, sort of garbage, but we know that there is no like proper garbage in C++. So anyway, it's also used for representing visual objects tree hierarchy. imagine that you have a lot of visual elements like items in QML or items in widgets, buttons, tabs and stuff. And all of the things in Qt are represented as a QObject trees. They also involved in events handling. Like, for example, if a user clicks their mouse on some widgets, it produces events, and then you can handle them in the program. So now regarding tree traversing, that's the main thing of this topic. There are roughly 4 active methods in the QObject interface now. All of the things are methods of QObject class. It's not clear from this slide, but it's done to just save some space. So the first method returns a reference to a list of only direct children of current object. The second one is used to find all children with a name specified based on options passed. So it might be either like recursive tree traversing or only direct children of the current object. The third one does the same, but uses a regular expression to match the name. And the last one is for finding only the first child with the name specified. And actually there are, I guess, 2 more deprecated methods in the interface related to the locating children. So, but some of them use, for example, old regular expression and will be eventually removed in Q6, I guess. So, and how findChildren is implemented. So it like traverses a tree, like breadth first, and collecting children on each level, then put them to the array. And if there are like some filtering criteria, for example, name or regular expression, not all of children will be collected, but only those are matched those criteria. So, and yeah, they are copied and put to the array, but not the objects themselves copied, only pointers to them. And now, I think there are some issues with this interface and with this approach. First 3 things are on this slide related to maintainability and extensibility and so on. The thing is that Qt gives some guarantees to binary and source compatibility between releases, and this is really hard to, for example, extend current methods or modify them somehow if, well, between releases and release cycle is too long, like a few years, not even 1 year, one release. And this is like really complicated to add something. Just imagine that we want eventually extend current method to accept a predicate instead of just a name. The 4th bullet here is extra copying of QList. I guess most of the time you don't really need to, I would say, copy something or hold a copy of all pointers. You just need to traverse, for example, to find something, or to just change names, or, for example, invoke a paint event or something like that. And you can avoid extra allocation and stuff, but I put this burning mark here because it's controversial, and at some point you really do need to preserve all children in a list, especially if the tree might be rebuilt during the iteration. Those happening, for example, when you need to partially repaint some widgets and tree hierarchy and then republish methods of widget, you can get this behavior. And the last one is the most questionable stuff. It was discussed in a list recently, like a few months ago. And why do we have like this tree or this hierarchy as a part of QObject at all? And why do we like have those methods in QObject class? So, but yet again, 3 Berlin marks, it's controversial and a lot of developers, a lot of meanings, and nothing, I guess, will be done here so far. And what can we do to like slightly improve or avoid all of those disadvantages? First of all, we can avoid extra copies of pointers or avoid extra allocations and reallocations. That's doable. The second thing, we can slightly clean up QObject's interface from the extra methods. And the last thing, we can slightly improve extensibility by making all elements composable. So we can, strictly speaking, like do this chaining or pipeline to compose a few predicates or a few actions in one chain and then evaluate it. I will show a bit later how to do that. So what do we have in modern C++ now, in C++20? We have two things in our toolbox. We have coroutines and we have ranges. I guess all of them, at least coroutines for sure, supported by 3 major compilers, MSVC, Clang, and GCC for now. There is a difference between supporting GCC and Clang, because in GCC now they are still under experimental section and require different flags, but I hope this will be unified soon enough. And ranges we also should have in C++20, at least it mentioned in CPP reference. I'm not sure, to be honest, whether this is fully implemented in any compiler. So here, if you want to play, I suggest to use some third-party libraries like ranges v3, originally written by Eric Niebler, or there are something in Boost, also written by the same person. So let's talk a bit about coroutines for now. So there were a lot of talks during past few years about coroutines, so I don't want to repeat all of them. Basically, coroutine in C++ and many other languages is a function that can be suspend its execution and resume it later. You can think about coroutines about sort of state machines that jumps between, when your program jumps between states based on some condition. And also important trait is the coroutines in C++ are stackless, which is like also a huge topic to discuss. But if you want to learn more about the difference between stackless, stackful, symmetric, asymmetric coroutines, you can read either Boost official documentation or there are something on CPP reference as well. But the point is that those coroutines are slightly faster and efficient in terms of memory. I'm talking about the stackless coroutines. So in C++, we, like almost as usual, have almost nothing for support them properly in terms of application development. We have those 3 keywords like await, yield, and return with weird prefix CO. And the first one just suspends current coroutine. The second one does the same, but also yields a value. And the last one returns value, and coroutine will not be resumed after that. So, but not everything that bad. And we have at least 2 libraries that give us good primitives for using coroutines. And first one is CPP-Coro, and the second one is Folly from Facebook. I personally recommend using the first one. I found personally it's easy to build and use. And there are a lot of things like generators, tasks, thread pools, cancellation tokens, and so on already implemented and for you, and yeah, ready to use. So now let's see the simple usage example. So here we have function iota that produces numbers, like for example 01, 2, 3, so number by number, and this function you can see returns generator from CPP Core and just yields numbers in infinite cycles. So this generator is theoretically infinite, but of course it's limited by ints capacity now. And here, after comment section, we have the example, so for loop that will print first 10 numbers. And yeah, we need this break here because the generator is kind of infinite. So here it is, and you can notice how this code is simple and looks natural, almost the same as a regular program we have. So now how we can utilize those things for lazy tree traversal in C++. And there are only two simple functions you need to implement. The first function is just check whether this is root or not, and if so, it's yields implementation function that recursively go down to the 3 and start yielding child by child. So it works like absolutely the same as the previous generator. So just yields values in a loop. And after that, when it exceeds all children, it's a tree, it returns a current child. So, and how it works in the explanation. So we have a tree here. Then after we ask about the first child, it goes down to the leftmost leaf and then yields the value to a caller and suspend. When we ask it again for the next one, it goes like up, level up, and yields value to a caller again and suspends. So we already can use it actually, like as a free function. So, and please notice that, okay, I'm going to use my fancy laser beam pointer. So here, I hope you can see it. Here at this point, nothing happened so far. I mean, nothing is evaluated. Our code doesn't go deep down to the leftmost leaf. So, but here, when we ask about the first element, only here it happens. So, and we can get the first child. And there is also a fallback I added because not all compilers might support this coroutines, and you might want to take advantage of this approach, for example, composable interface, that will be described later, without using coroutines. So, and fallback is this implementation without coroutines. It's the simplest one, and it's the closest possible to the original implementation we have in QObject now. With one major difference, I use stud vector here instead of QList or QVector because we don't really need implicit sharing here, and QList is not recommended for usage by Q developers. So, and you might notice that I use this parameter to return value. It's kind of bad practice, don't do that, but I tried to make it as close as possible to the original implementation because some compilers like clancar will too sly and perform some implementations and speed up code dramatically, and it's just not fair for benchmarks when we compete with original implementation. So now let's talk a bit about ranges. Okay, so what the ranges are? Oh, well, it's a next step after iterators. It's not true to say that it's just a wraparound two iterators. It's slightly more complicated, but it's for sure an iterable object. And ranges are composable, so you can use this pipeline operator to create this lazy pipeline, or it not necessarily have to be lazy, but it usually what you want to achieve. And as I mentioned before, this pipeline can be lazy, or you can provoke this evaluation midpoint you want. So let's say here is a simple example of ranges, of using ranges. And I introduced a few aliases here, R for ranges and V for our views. Here and this line, I'm just creating a view of 10 elements from 0 to 9. It's a half closed range. And at this point, just a lazy object kind of generator is created, but nothing is evaluated. So it does not return, for example, container like a vector of 10 elements. Here is a just lambda to check whether this function even or not, and then to apply square transformation to an element. And here we are creating this pipe with this technique, also known as a fusion and functional programming, I guess, because no intermediate states are created in this pipe. So, and then it prints like this, because ranges provide this overload for OStream operator, but it's kind of equal to the loop that would print elements. And the funny thing, so everything is lazy and this code is equal or, well, I guess super close to just a regular loop with a condition. So not just like that, but according to like memory consumption is super close in the logic. And the funny fact is a lot of developers after seeing that says, okay, why do we need using ranges at all? So we can use like this simple loops and this is fine. I mean, it's easier, no need to introduce any new conceptions, but it might be easier for this simple case, but ask yourself how often do you just iterating over ints in your program? That's usually more sophisticated pipes when you need to perform like harder transformation and so on, and those just might be expressed easily with this technique. So now ranges in the API, how we can add them to the QObject API and what we can get. So let's start with creating a new view. There are a lot of code, but it's quite simple, I guess. First of all, we want to create children view class that should inherit from special utility class that provided by ranges v3 library called viewFacade, and it's just children view of some type, which is by default QObject in our case. Here you should define some auxiliary functions just to this viewFacade have an access to all elements it needs. Then I decided to add structure for data that would hold a root object and the recursive generator from CPP Coro. We want to return from our previous implementation. And the thing is a structure called cursor. It's analog to iterator that just moving starting from the first element to the next until end, like a real cursor. This one we also should implement. And on this slide, some constructors are omitted. They are boring. Just accept some QObject and invoke the function to return generator. So now cursor function. First of all, our cursor will be like absolutely the same as an iterator. So, and here is an iterator of recursive generator from CPP Coro. And very few functions like read, then just dereference the iterator. Then function to move next, it's kind of Java style iterators function. So we just increment our iterator. And the last function we need to implement is the function to determine whether the end of the sequence is reached or not. this function accepts default sentinel t. And that's pretty much it. Also, please pay your attention that this cursor is single pass, which is important for iterating over tree, because if it was like multi-pass cursor, some codes, like for example codes and ranges, would try to take an advantage over multiple pass cursor. For example, that might use to pre-allocate some space when we transform in our pipe to a vector. And yeah, it's important to keep this cursor single pass. Nothing you can do in this implementation is single pass, because, for example, some functions are not implemented, namely like length, or functions to just check equality with a regular object. But you can explicitly specify that cursor is single pass just by defining some value in here. So yeah, that's it about implementation. And now let's move to the basic functionality. Ranges also provides a separate function called make pipeable. It's just a wrapper to nicely make your functions, like all callable objects, chainable. So we can use this pipe operator. And in our case, for children, it just returns, just accepts an object that might be like a pointer or reference to root object, and then returns children view. Yeah, that's pretty much it. So there are two functions. The first function for, like, pass through all children recursively, and the second one with the parameters. So you can specify whether you want to find only direct children or find children recursively. Now, how we can implement filtering by type, because standard functionality also supports it. Here we have implementation, again, super close to what we have in standard QObject. This one, we want to remove all extra things from T, like const qualifier, volatile, and pointer. Then we use a special method cast, which would return true if it's possible to cast object to this type. And then we pipe it to transform and just cast it to type if it's okay to do. And also, please take into account that the assumption is that we are working with QObject hierarchy, and in this hierarchy only class based on QObject are acceptable. So if you want to use it for different classes or for different hierarchies, you need to at least replace this one with a dynamic cast probably, or something like that. And yeah, it might be slightly more mess in implementation. Now, two more methods, two more chunks we can chain. Those are quite straightforward. So it's like by name, filtering by name. So we just return a filter view with some sort of predicate. And the same for regular expression. We just check in if the name has match, and that's it. So, and now let's talk a bit about usage examples. So now, since we have this fancy modern interface, we can do things like this. For example, I have some root object, then I'm creating a tree, creating some children, and then I can iterate over this tree like this. So only agent root by cute column children, and this code will be yielding children until there are some of them. And the second one is almost the same, but it stops when direct children amount exceeded. So now we can do several different filtering by type, name, or regular expression. And here, the first one, it's like we have here a chain, of children, and then we apply what we created before, the Qt column with underscore type of full star. And by the same manner, we can filter everything by name or by regular expression. And then I think is that those functions don't necessarily to be a part of library, or can be easily extended or added, because now you need only to add a small chunk. You don't need to modify the entire signature of function. And this is kind of cool. So, but from time to time, as I mentioned before, you need to make a copy of the things. And here, this lazy evaluation or lazy traversing is not super efficient, I would say, but not too less efficient, as we will say in a bit on benchmarks. So there are two methods. The first one is recommended for now. It's a crunches column to stud vector root pipe children. And the last one is you can just use plain cast, but this one is not recommended. So it's already, I guess, when I tried it last time, I got a compiler warning that this one is deprecated. So now the interesting thing, benchmarks. So I tried on the following test environment with kind of oldish Linux, but with a new Clang, I guess the newest available, and with the following flags. So Clang unfortunately required this studlib flag, and now without exception, because Qt itself compiles without exceptions, so they should be like more or less the same semi-equal conditions. And I added stud20 standard. So let's see. First of all, the first test was like passing through the entire tree and changing QObject name. The blue one is a regular QObject findChildren method. The red one is what we implemented, and the yellow one is the slowest one, but is expected when we want to also not only pass through, but also make a copy. So, and the interesting thing, you can notice that I implemented just experimental solution without any optimization, even intentionally from some point, but it works almost the same as a regular one in terms of time. So highly unlikely would you have hierarchies more than even 1 million elements, but typically it's like 500,000 and something like that. And this works like the same in terms of time. So, which is good. The second test I performed, I tried to filter it based on some criteria, like by type, and then trying to change name. So results here are not that good for the new implementation. So the blue one or the standard implementation is a bit faster even for small value, but still just benchmark, and I guess there are rooms to optimize a lot of things, even to create or use a custom allocator to preserve coroutine state and so on. So a lot of things to improve. And the last test, it's kind of funny. I just compared fallback tests I wrote with a regular implementation. And surprisingly, just eliminating QList container gives good result, especially for large number of elements. But for 1 billion is also kind of noticeable. So now let's talk a bit about pros and cons of the current implementation. So, like the first bullet is that they're easy to add a new functionality now. It's definitely a pro. So we can, even with this long release cycle of Qt, now it's possible to extend this functionality if you want, just add one more chunk and that's it, without touching interface at all. we got all these like advantages of functional approach. Operations are composable now, which leads to cleaner code and cleaner interface. All things are header only, so you can use even third-party libraries like ranges-v3 or cpp-coro. Those are header only, mostly, if you don't need some parts of cpp-coro. And this approach is lazy, so it's not evaluated immediately, only on demand. All of those things can be implemented without any additional libraries if you want. And the cool thing, the ranges and coroutines are officially available in C++20, so you can use them. Of course, there are a few cons, and the first thing is laziness, because as I mentioned, from time to time you need to create like the copy of the entire tree to prevent any hassle when it starts rebuilding, or some nodes might be removed, moved, and so on. Just imagine that you have like this coroutine suspended somewhere in the middle of tree, and then the tree itself starts rebuilding, so you can get dangling references, undefined behavior, and so on. The second thing is, well, it's really controversial because different users or programmers, they have different experience in terms of techniques, and not for all people it's not really convenient to use those approaches. The third one is like it's a fragile. It's kind of, I guess, depends on scenario you use. But as I mentioned before, if you use a lazy approach and then restart rebuilding, you're in danger. And the last one is not optimized for now in terms of speed and memory consumption. I would say I used Massive and it doesn't consume too much memory, I guess, but I didn't include those tests here. So, but yeah, there are rooms for improvement. So here I collected a few useful links. I will share the slides. All of the things are clickable. And first of all, I have, of course, experimental implementation you can play with. And there is also ranges v3. You can read it. That's a good one. Ranges documentation and cpp-coro and coroutines documentation on official CPP reference site, but I also recommend you to use Boost documentation. It's a good source of knowledge as well. So, yes, I guess that's pretty much it. Thank you for watching. And if there are any questions, just unmute yourself and shoot or post in Slack. I have it on the second monitor. Okay, sounds like there are no questions. So thank you again.